Okay, let's go to magnetic field and magnetic forces. To start with, let's go to a bar magnet. A bar magnet has two poles, north and south, and it's known that like poles repel and like poles attract in the same way as for charges. Like charges attract and like charges repel and like charges attract. Correct? Now, the steps are the same thing as for charges, right? Very similar. For example, to find the magnetic field, we do the same thing as we did for charges, right? To find the electric field. Remember, for the electric field, we use a test charge, right? To find the electric field of a positive charge or negative charge. Now, let's do the same thing using magnetic field. In this case, we have this permanent magnet, right, north and south poles. Now we need a test, in this case, a test magnet to find the magnetic field. The test magnet that is used right here is the compass. Okay, so we have a compass, correct? And by convention, we take this direction of the compass to be the north pole or the north seeking pole, right? North pole. That's the convention. Okay, now let's place this compass around this magnet to find the magnetic field in the way as we did for the electric charge. Okay, let's do it. So imagine that we place the compass right here. What happens? Well, we know that like poles repel and like poles attract. In this case, we have this compass is being repelled by north pole, right? Now we can go around. Later we can place the compass right here, goes in this way, right, in this direction, around, right, the magnet. And it's found that we create this magnetic field, right, or magnetic line. We have another one in this way, right, the same thing in the other direction, great, right? And in this way we form or we find the magnetic field. Then, as we know, magnetic field is a vector. It goes from north to south, right? North to south. This is by convention. Great. From north to south. Correct? Perfect. And also, we can do the same thing as we did for the electric charges, right? Remember Coulomb's law? If we use Coulomb's law, we know that we have two charges, positive, right, positive. Of course, they repel, but we have a force, right? This force, we use Newton's third law, are the same magnitude, right, in opposite direction. Also, we can find the distance between these two particles. And remember, we use Coulomb's law. Coulomb's law says that this electric force is equals to a constant K times Q1. Imagine this is Q1 and this is Q2. Q2 divided by the distance squared. We can do the same thing using the poles, right? The poles intensity, strength. Okay, let's go for the poles strength in the same way. In the same way, we can find that the force, in this case, the magnetic force using the pole is equals to K, a constant, right? Constant of magnetic proportionality in this case, right? Times, imagine this is P1, P2 divided by R squared. In this case, P, right? P1 and P2 are the pole's strength, right? Pole's strength. Correct? And well, they have the same form, correct? In this case, we're using the strength of the pole, right? Right here we have some strength 1 and strength 2, correct? At the poles. Perfect. Now, what happens when we're dealing with electric fields? Remember, the electric field we use, this is this quantity is equals to the force divided by the charge. We can do the same thing right here. Correct? So we have, in this case, the symbol for the magnetic field is H, right? Should be equals to the force, right? The magnetic force divided by the pole strength, right? Also, we define, right, this magnitude to be k times the charge times r squared. Correct? That's another form for the electric field. Now let's go to the magnetic field in the same way. Correct? The same way. We have that this is equals to k, the constant, times the pole strength divided by r squared. Okay, now this is the at the beginning the way to work with magnetic fields, right, and magnetic forces. But later it was found that actually the magnetic field is produced by charges in motion. So it's better to study, right, the magnetic field using charges in motion or current and find the interactions with these currents and the magnetic field. Now that's the study that we are familiar with today. Let's do it in this way. Okay, perfect. Again, let's create a constant magnetic field. It's very important, right, to start with a constant magnetic field. And the same thing, the same way as we did for charges, right? We studied, right, the electric field using constant, the beginning constant electric field. Now, let's create a constant magnetic field. How we can create a constant magnetic field? Well, in this way. Imagine, let's start with the electric field to compare. We remember for electric field we use this huge plate, correct? This is positive, correct? And this is negative. And then when we have that inside, we create a constant electric field. Let's do the same thing for a magnet, right? Or magnetic field. We have a huge north pole right here and a huge south pole right here, correct? Now we create in between a constant or very close constant magnetic field. And remember, magnetic field goes from north to south, north to south, north to south, north to south. The symbol for magnetic field is V. Okay, perfect. Using charges. And using poles, we have H. Now it's gonna be V, the symbol for the magnetic field. Perfect. Now imagine that we have this constant magnetic field, correct? And we have a charge at rest. If we have a charge at rest, nothing happens to the charge. Now let's set this charge into motion with some velocity. When we have some velocity, remember the charge in motion produces or induces a magnetic field. That magnetic field produced by the charge in motion interacts, in this case, with an external magnetic field. And we have interaction, we have forces present. Now, it's found by the experiment when the velocity is parallel to the magnetic field, nothing happens. Nothing happens to the charge in motion, right? It keeps moving in constant speed. But what happens if the charge moves perpendicularly to the magnetic field? In that case, I found that this charge experiences a force. That force is perpendicular to the magnetic field, is also perpendicular to the speed. Got it? Now, let's create these conditions right here. Imagine that we're looking for the force that experienced by this charge. We have, by convention, the positive charge, correct? So it's found that it's proportional to the charge. If we increase the charge of the particle, right, inside of the magnetic field, right, the force increases. Now also, this force is proportional or inversely proportional to actually it's proportional to velocity. If we increase the velocity, we increase the force experienced by that charge. Also, it's found that again, when the velocity is parallel to the magnetic field, nothing happens. But if we increase the angle, right, and we go to 90 degrees, we get the maximum force exerted on this charged particle in motion. Okay, so means that this force depends also on the angle, right? Now we need to find which function relates this condition. When it's parallel to the magnetic field, we have zero value, and when it's perpendicular, we have the maximum. The function that is found is sine. When the angle is 0, sine 0 is 0, and sine 90 is 1. Correct? So this force is then also proportional to sine of the angle. Right? Now remember, these are factors. These are factors for the force that is experienced by this charge. Then we can multiply all of these factors. So the force is proportional to charge times V times sine theta. Okay, but we need to eliminate this symbol. Remember, we don't want this symbol, we need an equation. So to do that, we use a constant, the constant of proportionality. It's found that that constant is gonna be the magnetic field. The magnetic field in this case is constant, so that's gonna be the constant of proportionality. So in this case, the force is equals to the constant, which is B, magnetic field, times the charge. In this case, we use just the magnitude of the charge. Right? We can use the magnitude of the charge times V times sine theta. Look, by this force, we mentioned at the beginning, this force is found to be perpendicular to the velocity and perpendicular to the magnetic field. To represent this, usually we use the right-hand rule, right? This is my right hand, this is my right hand. Now, let's represent these fingers to be the magnetic field, and this right thumb to be the direction of the velocity. So this form a plane, magnetic field, right, and the velocity. Now the force is gonna be perpendicular to this plane in this way. Right? If the magnetic field goes up and the velocity goes in this direction, so the force experienced by the charge is gonna be perpendicular to this plane in this way, correct? Always perpendicular, in this way, in that way, right, in that way, correct? Perfect. And this is again the formula that relates the force, right, on a charge when the charge is moving inside of a constant magnetic field, sine theta, correct? Perfect. Now we need the unit. We need the units for the magnetic field. In the units, well, the units we have two units. One is Tesla and the other one is Gauss. Okay, but the unit at the beginning, unit for B, right, is gonna be Weber divided by square meter. Correct? It's gonna be equals to Weber divided by square meter, and this is also called Tesla, right? So the unit is Tesla, and Tesla is just what? T, and this equals to what? Equals to Weber over square meter. Also we have the units called Gauss, right? This is Tesla. Okay, what else? The second one is gonna be Gauss, right? Per G. And this is equals to, we have another unit which is Maxwell, in this case Maxwell divided by square centimeters, right? Equals to mx over square centimeters. And one Maxwell is one line of force. Remember when we have the magnetic field for a bar magnet, correct, north-south, we found, right, that this is the representation of the magnetic field. And these are called the same thing as for electric field, right, the line of forces, or in this case, the magnetic field. And one of these lines is called a Maxwell. So Maxwell. One line is one Maxwell. Correct. Now these two are related in this way. These two units, 1 Tesla is equals to 10 to the negative 4 Gauss. And also to have an idea, one Maxwell or one Maxwell is one line, right? What about one Weber? Weber is equals to 10 to the 8 Maxwell, right? So this lines is gonna be in one, right? 10 to the 8 lines per square meter. Okay, that's one Weber. Perfect. Now let's go to we found that this is the force. It will happen if we involve also the electrostatic force, correct? Remember the electrostatic force is equals to electric field times the charge, correct? And by the way, look, every time remember that we have sign and vectors, we can represent this using the cross product, correct? Like in this case, so it's gonna be equals to the charge, right, times V cross B, correct? Now the same thing happens in this case. This is only using the magnetic forces. Now what happens if we introduce the electric forces? Well, and then we can find the total force than on a charged particle. Well, in this case, should be the total force gonna be this force, correct? The electric force plus the magnetic force, which is charge V cross B, correct? Which is the magnetic force on the charge. Perfect. So should be then the total force, charge times the electric field plus this cross product, correct? That's the total force. This force is also called the Lorentz force. Okay, great. Now we have some conventions also to represent the magnetic field. It's easy. It's easier to represent this in this way because the magnetic field is in 3D, and when we are representing, for example, the direction of the force, it's hard to visualize it in 3D. It's easier we have only 2D, correct? And you see this convention. Imagine that we have a arrow, right? This is the arrow right here, correct? Imagine it goes in this direction, okay? And we have this is the tail, right, of this arrow like that. Okay, you are on this side, correct? And you're looking to the arrow, right, coming toward you. You will see, right, the tip right here, the tip, right, circles, right, circles. Okay, and this is a representation. Then imagine that we are right here, and the arrows are coming toward us. So we see the tips on it, right? First, another representation for a field, a field that is out of the page, right? This is field B, field, right? It's coming out of the page, correct? Again, this is the magnetic field. Now what happens if we are right here and we see the arrows going away from us, so we see only the tail, right? The back of the arrows. And what do we see? Well, we're gonna see this cross that represent the tails of the arrow in this case, or the vector, correct? And this is again the magnetic field. One more time, we are right here, and we see the magnetic fields going right into the board. So that should be the representation for the magnetic field. And this is B field into the page, correct? Into right, the page or the board in this case. Now, for example, imagine that we have a charge moving in this direction with this velocity. We can use the right-hand rule, right, to see the path for this charged particles inside of this constant magnetic field. And that's the way. In this case, look, we see that the fields coming out, right? And we see that the velocity goes in this way, right, to the right. What should be the force acting? What should be down, right? Should be down. And then the path for this particle should be a circular path, right, clockwise. What happens in when we have this type of magnetic fields, right? The magnetic field goes into the page, into the board, the same thing. We use the right hand rule, correct? And now the magnetic field goes inside. Remember, these fingers represent the magnetic field. So the magnetic field goes inside. The velocity goes again to the right. Now the force, again, is perpendicular to this plane. This is a plane, right? Should be in this way. The velocity is constant, so means this produces a circular path. Correct, circular path. The force, the magnetic force produces only the change in the direction of the velocity. It doesn't act on the magnitude. Okay, so meaning that we create a circular path when we're dealing with magnetic forces. In this case, the magnetic forces, right, when that positive charge is inside a constant magnetic field. Correct? Perfect. Also, we use the right hand rule when we're dealing with current. Imagine that we have a wire. Imagine that we have a wire with current. Imagine we have a wire in this direction, right, and we have current in that direction. One more time, how we can find the magnetic field? Well, we use the right hand rule. This again represent the magnetic field, and this represent the current in this case, right? So the direction is doing this way. We bend, right, the fingers that represent the magnetic field, and this is gonna be the current in this way. So we have then this is gonna be the magnetic field, correct? The magnetic field, and in this case it goes in this way, right? In this way, in this direction. Remember, it has direction, correct? At each point, right, we have concentric lines that represent the magnetic field. And you can see the magnetic field from a circular path, correct? It's not like the electric field. The electric field is starting one charge and ends in the other charge. Right here, right, they form loops, circular loops. Okay, perfect. Also, look, we mentioned that the cause of a magnetic field is, what causes a magnetic field is a charge in motion, like a positive charge, right? Now, imagine that we have a charge that moves in this direction, correct, with some velocity. Means that at some distance right here, we have the magnetic field, right? The magnetic field is produced by this charge in motion, right? But right here at this distance also, the magnetic field is being changing. Every time we have a change in magnetic field, right, it's found that along this path, correct, we have this magnetic field also behind, because behind also is changing, right, the magnetic field, right, in this way. Imagine, for example, that we simulate this magnetic field using this magnet, right? Imagine this is what? This is north, this is south, right? And we have, right, that this is the magnetic field. Imagine, right? And now let's move this charge, this magnet, right, in this direction, right here. Of course, at this distance, we have magnetic fields. Even magnetic field is not so strong, but still present, right? When this moves, right, we have a change, and we have, right, the magnetic field changes. The same thing happens right here. The magnetic field changes, correct? We apply this idea right here. This is where it's moved, is a magnetic field, right? And right here, the magnetic field is created, And then right here, we have the maximum change, right? Changes and changes, right? And that's the way how the magnetic field is created, correct? Using the right hand rule by convention, to represent the direction of the magnetic field. Okay, perfect. Now let's go to the next topic, which is magnetic flux. Magnetic flux is the same thing as for charges. Okay, remember before we found the electric flux. Now right here is gonna be the magnetic flux. Okay, magnetic flux, magnetic flux. Right, the symbol is phi, right? B. Correct, magnetic flux. Perfect. The same thing as for again for electric field, right? Imagine that we have now a magnetic field. Magnetic field, correct. Magnetic field, for simplicity, is constant, and we have a funnel right here. A funnel is used to collect the magnetic field. Now this is the area, right, of the opening, and in this case we take this area to be a vector. It has a magnitude, it has a direction, right? This is the direction. This is the direction of the of this area, right? This is the magnitude, area magnitude, and this is correct the direction of the area. Now it's found that the magnetic flux, correct, is proportional to the area. If we increase the area, right, we increase the magnetic flux. Also, look, if we change the angle, when the magnetic field is parallel to the area, we have the maximum flux, magnetic flux going through this area, through this opening. Now, what happens if we rotate the funnel, right, and later the magnetic lines, right, is perpendicular to the direction of the area? Well, in this case, we have zero magnetic flux going through this opening, correct? And one more time, the magnetic flux depends also on the angle, right? When the angle is 0, we have maximum, and when the angle is 90 degrees, it's gonna be 0. What should be the function that help us to do that? Well, cosine, right? So phi b is proportional to cosine theta. Now let's one more time start factors. Multiply these two factors, and it's gonna be the magnetic flux proportional to area cosine the angle. One more time, let's eliminate this symbol, correct, and add a constant. The constant is added is the magnetic field, because magnetic field is constant in this picture. Perfect, so gonna be the magnetic flux is equals to the magnetic field times the area times cosine theta. Correct? Okay, we have another equation right here, and this is for the magnetic flux, cosine theta. Also remember, because we have cosine, we represent this as the dot product of b, right, vector b, right, vector a, and that's gonna be the same, right, the magnetic flux. Perfect. Also we can use integrals, the same thing as we did for charges, right? We can find the magnetic flux using the integrals b magnetic field that the element of area. Correct? Perfect. Also, using this new quantity, we can find the units for the magnetic field. The units also is found from here, right? We mentioned that the unit is gonna be Tesla, and it's gonna be what? It's gonna be Gauss. Also, look, we can represent the units of Tesla in function of, right, in the metric system, correct, using newtons and meters and so on. For example, for number 1, we have that B is equals to force divided by charge V, right, sine theta. Let's see, what should be the units for force? Well, the units for force are Newton, the units for charge, coulombs, the units for velocity, meters per second, right, meters per second. Now let's move this, arrange in this way, like that. So coulombs per second is 1 amp, right? So this equals to newtons, right, amps per meter. Correct? That should be 1 Tesla, right? So 1 Tesla is equals to newtons, 1 Newton, right, per amp per meter. Okay, now let's go back again and use this quantity for finding the units. Okay, using this quantity right here. So B now is gonna be equals to what? Gonna be magnetic flux, right, divided by the area. And what is the units for magnetic flux? Well, we have 2 units. We have Webers and we have Gauss. Correct? We can use Weber, right, as we did at the beginning. Again, this is for unit, and this is called Tesla. Correct? It's called Tesla. Correct? Now, if we use centimeters instead of meters, so in this case we use the units gonna be Maxwell. Remember, one Maxwell is 1 line of the magnetic field divided by square centimeters equals to 1 Gauss. Correct? And because of this, this represents a density, right? Because divided by area. So this is also called a magnetic field is also called the magnetic flux density, right? Magnetic flux density, magnetic, right, flux density. It's another form to represent the magnetic field, right? Magnetic flux density. Okay, perfect. Now imagine that we're looking for the magnetic flux in a surface, correct? In a surface, a closed surface, for when we apply, for example, the Gauss law. So it's found that for a closed surface, this product is just equals to 0. Okay, perfect. Now let's see how is the motion of a charged particle in a magnetic field. You already found some motion, right, when you use the right-hand rule. Now let's continue in this analysis. Imagine that we have the magnetic field, right, which is constant. Correct, so the magnetic field, imagine it's constant. When we say that it's constant, it means that they have the same magnitude, the same direction, correct? When we say the same magnitude, the space between these lines is the same, it's constant, correct? And the direction is down, all of them is gonna be constant, the magnitude is constant in direction. Okay, perfect. Imagine that we have a charge right here. If the charge is at rest, nothing happens. Well, because it has only a electric field, correct? Now this charge to interact with this magnetic field, this charge must possess a magnetic field. The magnetic field now must interact with this external magnetic field. And how does this is produced? Well, when this charge gains some velocity. Imagine it gains some velocity. Now, when the charge is moving, it produces a magnetic field. The magnetic field produced by this charge interact with this external magnetic field, and we have forces. Remember, when we have interaction, we have forces. Forces are interactions or collisions and so on. Okay, perfect. Now, in this case, we have that this moves right in circular path, right? And we have the force acting right in this way. Mine is a circular path, isn't? Well, it's gonna be in this way, the circular path. Okay, gonna be like this, correct? In this way, imagine that's the force acting, right? So as you can see, in this case, it's hard to see it, but when we use, right, this convention, right, that this is the electric field, magnetic field going inside, correct? And imagine we have a charge right here, positive charge. We have a velocity, right, produced by a circular path. In this way, we have the force. The force changes only the direction of the particle, correct? And that force is coming using this equation right here. Perfect. This is again how the particle moves inside of the magnetic field. One more time, correct? We have, this is the magnetic field, correct? We have a particle right here, it moves right in circular path. Imagine circular path, correct, in this way. Perfect. So we have right here, we have velocity, right, and we have force. Right over here we have force and we have the velocity, correct? Let's see, because this is in circular path, correct? The net force, and because the speed is constant, so the net force must be equal to the centripetal force. Remember that from mechanics, right? Circular path, the net force is equals to the centripetal force, and centripetal force equals to mass b squared over r. Correct? Now, but what is the force that make this charged particles move in circular path? Well, that force is gonna be this force. Correct? And well, then means that centripetal force and b squared over, let's use this r, r, right, which is the radius of the circumference, okay, must be equals to q, right, v sine theta. But what is the angle between this angle, right? Remember, it's gonna be the angle between the magnetic field and the velocity. Okay, let's do it. The velocity goes in this direction, the magnetic field, right, goes inside, so the angle is gonna be 90 degrees, correct? Sine 90 is equals to 1. It's equals to v charge v. Imagine that we are looking for r, right, the radius, the curvature from here, r is equals to what? Let's use cross multiply, it's gonna be m v squared over b charge v. And what do we have at the end? Well, this radius of curvature is equals to mass of the charged particles v, because this v is cancelled with this v, divided by the magnetic field intensity times the charge. Correct? Perfect. What happens if we have now this situation? Imagine that we have a capacitor, right? Capacitor, remember the capacitor produces a, imagine it's positive, right? Negative. Produces a magnetic field in this direction, correct? Electric field, actually, it's electric field. Now imagine that we place this capacitor inside of a magnetic field. Magnetic field. Let's combine them. Okay, now we have a charge in this direction. Again, charge in that direction. Remember, if we have only a electric field, correct, the path of the charge should be in this way. But we have the magnetic field is in this direction. The velocity we have a force, the magnetic force going up. Look, the magnetic force going up and the electric force going down. What happens when these two forces are the same, right? The force done by the electric field and the force done by the magnetic field. In that case, right, the particle moves in a straight line. Correct? And what do we have? Well, we have that this electric force is equals to this magnetic force. So what should be the electric force? The electric force is the charge times the electric field, and equals to what should be the magnetic force? Well, The magnetic force is coming using this equation, correct? B charge V, and then the angle between the velocity, this is V, and the magnetic field is 90 degrees, correct? So sine 90 is gonna be 1. From here, we can find the velocity, correct? The velocity of this charge, right? And the velocity is gonna be equals to what? Velocity, the charges cancel, so velocity is equals to the electric field intensity divided by the magnetic field intensity. Okay, so we have this equation that is found when the electric force is the same as the magnetic force, and we have this situation, correct? Actually, this formula is used to find the speed of light, right? We call this the speed of light. Speed of light is coming in that way. Okay, perfect. Great. Now let's go to the case when the velocity is not perpendicular to the magnetic field, like in this case. The velocity of the particle, right? Imagine that we have this as the magnetic field, right? Magnetic field is constant. Now the particle is moving with this velocity, right? In that direction, correct? So I mean it has a component in the parallel to the magnetic field and component perpendicular to the magnetic field. Remember, when it is perpendicular only, we have a circular path, right? Circular path, like that one that we found before, correct? Remember, if this is perpendicular, correct, we create a circular path. So if we have only this, it should be a perpendicular path, correct? Sorry, a circular path. But what happens when we add the extra component? Well, in this case, we have a helical motion, right? One more time, imagine, again, this is the electric field. In this case, the charge has, the velocity has an angle, right, with respect to this magnetic field. So we have this motion, right, in this way. It has two components, right? One component perpendicular, one component, right, parallel to the magnetic field. This is the helical motion. Okay, helical motion. Now let's involve the excuse me. Let's involve the these quantities, correct, to find an equation that help us to analyze this type of motion. Okay. So if we have that R, right, R is equals to M, this R right here, correct, equals to MV over the charge, right, times B, correct. And also we know that when it's circular path, right, this velocity is equals to M is equals to R times omega, or maybe for circular motion or rotational motion, correct? Now from here, we can find that omega is equals to what? Let's do it. Let's see what happens. So what do we have? We have that this is R is equals to mass over charge over B, but V is equals to R times omega. Correct. Now R is cancelled. We have that omega is equals to charge times the magnetic field divided by the mass. Correct. Okay, perfect. Now from here we can define. Remember how to define omega also equals to 2 pi frequency. In this case, the frequency is called the cyclotron frequency. Okay, Also, from here we can find the magnet, the period, right? The period when we have a particle moving, right, in circular path along this magnetic field, and we can find the period. How to find the period? Period is equals to, remember, this is equals to 2 pi over period, correct? So the period is equals to 2 pi over omega, but omega is equals to this quantity, so it's gonna be then period is equals to 2 pi times what? Times mass, correct, divided by the charge times the magnetic field, correct? As you can see, the period doesn't depend on the speed, the velocity, right? Doesn't depend on the speed, correct? And doesn't depend on the radius either, right? That depends on what? On the mass, the charge, and the magnetic field, correct? Perfect. So that's the period in circular path. Now, what should be the velocity in this direction? From here to here, v. Okay, so we can find that v, right? That velocity is gonna be v is equals to what? This distance, right? The distance divided by what? By the time. But the time is equals to what? The time is equals to the period, right? It's periodic. So it's equals to that distance equals to the time is equals to the period, correct? And then we can find this distance, right? Actually, the distance d, correct? This distance, that distance, and also we can find, well, okay, that distance is gonna be v in this direction. V, let's say v what? V parallel. Okay, v parallel, correct? Correct. And what should be this v parallel? Is equals to this distance, right? D, the distance from here to here, correct? The distance divided by the period. By the period is equals to 2 pi m over charge over v, correct? So it's equals to, again, charge v, the distance divided by 2 pi m. So we can find again that velocity, or if we know this velocity, we can find the distance between two let's say these 2 points, right? That produces one period. Okay, and one more time, this frequency f, is called the cyclotron, correct? Frequency. Perfect. Well, with this, we finished this first half for this chapter, magnetic field and magnetic forces, and let's go later for the second half for this chapter. Okay, thank you, and see you in the next video.